We flip a switch and light fills a room. We plug in a phone and its screen comes to life. But if you look past the utility of everyday electronics and focus on the physical reality inside a solid wire, a strange mystery emerges. What is actually moving through a completely solid piece of metal? This animated diagram gives us a way to measure that hidden movement. Imagine a translucent wire, and inside it we set up an invisible checkpoint, a flat, glowing disk slicing right through its cross-section. Particles carry electrical charge forward and backward across this boundary. To find the net charge, represented by the letter Q, we count the amount of positive charge flowing forward, and then carefully subtract any negative charge flowing backward over a specific interval of time. If that flow is constant, we arrive at the baseline formula for steady current. Current, or I, equals the net charge Q divided by the time interval, T. It is simply a ratio of charge over time. In the International System of Units, we measure this rate in amperes. The natural scale varies wildly. An average lightning strike carries tens of thousands of amperes, while the electrical signals firing through your own nerves right now measure in tiny microamperes. So, macroscopic current is a strictly measurable rate of net charge flow over time. It is a precise mathematical accounting of movement across a boundary. But this raises an immediate question. Since bulk matter like a metal wire is packed with incredibly dense, highly energized particles, why don't you get a shock every time you pick up an unconnected copper cable? This diagram reveals the microscopic structure of a metal conductor to show us why. It consists of large, tightly bound, positively charged ions surrounded by a sea of tiny, negatively charged electrons that are free to move within the bulk material. Thanks to ambient thermal energy, these free electrons do not sit still. They zip around at incredibly high speeds, constantly colliding with the fixed positive ions and bouncing off in completely random, unpredictable directions. Because this high-speed motion is entirely chaotic, there is no favored direction. For every electron moving to the left, there is, on average, another electron moving to the right. The net flow perfectly cancels out. Immense, chaotic, microscopic motion does not equal directed macroscopic current. Without a unified direction, the net electrical flow remains exactly zero. This diagram shows how we force a unified direction. We attach two colored disks to the ends of the wire, one packed with positive charge, the other with negative. This immediately generates electric field lines pointing straight through the metal. The field applies a directed force to the free electrons. They are still vibrating and colliding randomly, but now the whole chaotic swarm starts to slowly, collectively creep toward the positive disk. This unified, slow creep against the thermal chaos is what we call electron drift, and that physical drift is the actual electric current. But there is an inherent flaw in this setup. As the drifting electrons arrive at the positive disk, their negative charges neutralize the positive ones. Once the charges neutralize, the electric field rapidly dissolves. No field means no applied force, and without that force, the electrons instantly revert to their random thermal chaos. The forward drift stops completely. An isolated electric field creates a current for only a very short while, a temporary spark. To extract continuous power, we have to find a physical mechanism to maintain the flow. What prevents this rapid neutralization? What physics mechanism is required to forcefully maintain that field and keep a device running smoothly? This diagram illustrates the solution: a battery. Think of it as an active charge pump connected to the ends of our wire, forcefully pulling electrons away from the positive terminal and pushing them back out toward the negative one. The battery supplies fresh charges just as fast as the moving electrons neutralize them. The electric field remains stable inside the conductor, locking the whole system into a continuous, steady state. However, in complex real-world circuits, currents are rarely this perfectly steady. They fluctuate, ramping up and dropping down from millisecond to millisecond. To accurately describe a fluctuating flow, this visual shows how we apply calculus. We shrink the timeline, taking the limit as the interval delta t approaches zero, measuring the flow across a microscopic, frozen slice of time. This gives us the final formula for instantaneous current, I equals dq over dt. We are no longer looking at an average over a long period, but the exact rate of charge crossing the boundary at a specific instant. Electric current is mathematically measured drifting charge. It is a calculated rate of flow, fighting against constant microscopic chaos, driven continuously forward by an unbroken electric field.